In this video, we're going to do some more linear modeling. And in that linear modeling, we're going to be working with very large data sets. We're going to let Desmos at desmos.com do a lot of the heavy lifting for us. So we're going to be fitting models to data. We're going to be working with the linear regression, which is finding the best fit line for the data. And we're going to look at a correlation coefficient, which is a number between -1 and 1 that gives us some information about the strength of the best fit line. Let's go ahead and start with an example. So we're going to start by opening the US COVID cases. So I've got the COVID cases in a spreadsheet. If you are in the Canvas classroom, you can open that from here. If you're not in the Canvas classroom, you can go ahead and click on the link in the worksheet. So I've got the cases here, and they span from day 1, which is back in February, up to, I believe this data set goes to September 13th. And this is from the New York Times data set. Okay, so you'll see that on September 13th, 2020, 230 days into the pandemic, we've got about 6.5 million total cases and about 194,000 deaths. So some pretty sobering numbers. What we want to do is to graph the days and the total number of cases. So I'm going to go up to the very top. I'm going to grab this first day 1, and I'm going to click Shift and then arrow and then the down arrow. You can also do page down, but I'm just going to go all the way through this data. You can do this with your cursor as well, but I'm highlighting all of the data. I'm not grabbing the names though, because Desmos doesn't know what to do with those names. Okay, so once I get down here, you can either do edit and then copy, or you can do a Control-C. Your browser might even let you right click on your mouse and copy from there. So I'm going to copy that data. Looks like I need to open up Desmos. So I'll just go to desmos.com, graphing calculator, and my cursor is in an empty cell. All I need to do is to do a Control-V to paste. So it pasted all 237 data sets. And it's given me a pretty decent look at the data. And it looks like there's actually 3 different trends here. So as you're looking at the trends, we have a very, very slow growth, which increases very, very quickly here. So this is an exponential growth. But once it turns the corner, we have linear growth here. The linear growth starts at about day 70-ish, and it goes through and then changes direction to about day 154, and then we have a different slope. So we've got one slope here and a different slope after about day 154. So we've got a couple of different linear models that we can fit to the data. We're not going to do the exponential model, but there would be an exponential model for this first bit. And just very coincidentally, the exponential model fits until about April 1st, which is when most of the country was doing a shelter-in-place quarantine. So back to our data. We're going to grab the data instead that goes from, and I've marked these so I wouldn't forget, up. Let's see. So it's about April 1st. So like I mentioned, we were on day 70, I think, which is what we estimated. Day 70, day 72, this is the start of the national quarantine, even though it was state by state. The majority of states here were in a shelter-in-place quarantine situation. And it went through today, and I've got an asterisk next to that one as well. So I'm just going to choose these, just selecting them, highlighting them so I can copy and paste them in. Today 150. So it goes to about the middle of June. So again, coincidentally, in the middle of June, this is when school is out. This is when the weather starts to get really nice and people are a little more lax in terms of social distancing. Okay, so I'm going to go ahead and copy this data. So Control-C to copy, or you can do an edit copy. Back to Desmos. I don't want all of the data. I'm just going to click X to get rid of it. I'm going to put my cursor in this empty cell and do a Control-V. Now I've got just very linear looking data. I You can even zoom in on it if you want, but you can see that I've got a pretty nice linear data set. And this is from April 1st, the start of the stay-at-home orders, until about the middle of June. So we have a pretty nice looking data set. Let's go back to our worksheet. Estimate the first interval of days where the data is linear. So we've done that already, and that was days 75. Let me go back to Desmos. 72 to 150 are the ones that we're using. 72, if you were doing this worksheet on your own, you could choose slightly different days. 72 and 150 just works out pretty nice here. Graph just this data, and we've done that. Next, we're going to find the linear regression. Desmos does a really nice job of finding the linear regression. Regression is the equation that fits the data really nicely, and it is going to give it to me in the form of y equals mx plus b, but I want to estimate my data. And if I go back to Desmos, it has labeled my x's with an x sub 1 and my y's with a y sub 1. So into Desmos, I'm going to say y sub 1 is approximately, I'm going to grab the tilde from above my tab key, m x sub 1 plus b. So we're going to go back into Desmos. This tells Desmos that we want to find a line that fits the data from the table with x1 and y1. So y, and I just type 1 after it, it automatically subscripts. So 1, and then I want to grab tilde, which is next to number 1 on your top row, second to top row. M x1, again, just type 1, it automatically subscripts, plus b. Here's my line, and it really fits it pretty well, right? Not exactly. We needed a few days to kind of catch up to the linear relationship here, but it gives me the values for m and the value for b. This is a huge number, times 10 to the 6th. That's in the millions. So let's go ahead and move this over. I'm just going to shrink this down and give it its own window so we can get this into our worksheet. Okay, I think I can still see it there. And then back to our worksheet. So I want to grab the numbers off of Desmos. So the linear equation. So I am using y equals mx plus b. M is 25,064. So y equals, let me get a slightly smaller, m 25063.4. And let me just erase this so I've got a little more room here. Plus, or x, I should say, plus b. Negative 1.502 times 10 to the 6. So I have 6 decimal places after the decimal place between the 1 and the 5. So I do need to change this plus to a minus. Minus 1,502,00. So that's going to give me 1, 2, 3, 4, 5. I need one more 6. So I have 25,063.4 minus 1,502,000. So this is my best fit line for these days. Now, Desmos does a really great job of just coming up with this data, but what it's done is it found M for us. M is this number. M is a very specific number. It's my rate of change. So this is my rate, cases per day, 25,063.4 cases per day that were increasing, because this is a positive slope, in the US. My y-intercept is not that interesting because we're never going to have, unfortunately, well, it wouldn't even make sense, a negative number of cases. The other thing that we're asked for is the correlation coefficient. The correlation coefficient is this number r over here. We're going to work with r and not r squared. This is actually the r number to the power 2, but we're going to work with the r just as is. So that's 0.9973. 0.9973. 3. So to review how we did that, let me make this large, and then we'll do some more examples and kind of fit everything together. In Desmos, the linear regression formula is y1 approximately mx1 plus b. These numbers right here could change. They could be 2 or 3, depending on how many tables you have in Desmos. If you're always starting with just one table and then erasing it, it's going to go back to x1 and y1. But these numbers right here should be whatever you need to match the table. Match table of data. Okay, the correlation coefficient. We're looking for the value r. R is a number between -1 and 1. So R is the correlation coefficient. It can be as small as -1, R, and as big as 1. When we're close to 1, this is a positive linear correlation, meaning that the line goes up, has a positive slope, just like our data did. If we're close to -1, this is going to be a negative linear correlation, meaning that the graph goes down, which in our case, it did not go down. We actually need statistics to test the strength of the correlation, but for ours, let me grab Desmos again. For ours, we were really, really close to a positive 1. 0.9973 is a really strong linear correlation. The highest that our number can be is 1. Okay, let's go back to the information here. Next, we're going to look at student data. We're going to graph a scatter plot of college credits and age. I've got the student data here. This is data that was gathered from a summer statistics class. I just have them take a survey, answer some questions, so we have some data to work with throughout the quarter. So I've just borrowed that data. We want to plot college credits and age. So the question is there a linear relationship? Is there a relationship at all? Does your age make a difference to how many college credits you have? So you might suspect that the older you are, the more college credits you might have. So let's take a look. So I've highlighted all of this data. I did not grab the names, college credits, and age. Sometimes that messes Desmos up. I'm going to do a Control-C to copy, or you can do Edit and then copy, maybe even right-click and copy. I'm going to go back to Desmos, if I can find it. See, I have it in another screen here. So I'm going to go back to Desmos. Let's make this large. And I'm going to get rid of, scroll up there. I'm just going to get rid of my table and linear correlation or linear regression. I'm going to do a Control-V. Notice how it put those back at X1 and Y1. Not a great scatter plot here. It still has the old scale here for the y-axis. So let's go ahead and make that scale a little bit better. If I go to my settings by hitting the wrench, my x-axis, these are my college credits. So it's going to range anywhere from 0 to, we've got 145, 184. Let's make that go up to 0 to 200. And then age, I don't think we're going to have anybody younger than 10. So let's say 10 to, we've got a 47. Let's say 60, just to grab as many as we can. Okay, so I want you to compare this with the graph that we had for the COVID cases. The graph of the COVID cases was nice and tight, right? We had a linear growth that went from April to the middle of June, and then it was slightly steeper after that, but all of the points were right next to one another. That is not the case here. These are so much more scattered. We're going to go ahead and find the linear regression, or Desmos is going to find the best fit line for us. I double check my subscripts. They are ones. So I'm just going to put in y mx plus b, but I'm going to put it in the regression form, y1. I'm going to grab that tilde, so shift to get tilde right up to my number 1. mx1, whoops, 1 automatically subscripts plus b. Okay, so I want to go over here. Take a look at that R number, that correlation coefficient. It is not close to +1. It's only 0.17. It's slightly positive. There's maybe a tiny correlation. The older you are, the more credits you have. But I don't even know that we can say that that's meaningful in any way. We only have 0.17 for our correlation coefficient. Let's go ahead and put this into our worksheet. I just want to move things a little bit so I can see everybody. Okay. So, does there appear to be a relationship? Not really. They were really scattered. Those points were not close to one another at all. So I'm going to say no. These were really scattered. We were able to find a linear regression equation though. So that's going to be y equals, I can move this up. We'll go there. Okay, so y equals M is 0.039, we'll call it 0.039x plus b plus 22.54. Y was age, so you might also want to write it as age of college credits is equal to 0.039 college credits plus 22.54. What is the value of the correlation coefficient? It is 0.1706, very, very small. It's not even close to 1, so it's not close, to 1 or -1. Instead, it's close to 0. So we're really finding no correlation here. I'm just going to write CORR. No relationship, is just scattered. And if you take a look at what we've got here for part C, I just found a really nice graphic that goes through and shows you what a perfect negative correlation looks like. This is an R value of -1. You can see how the best fit line has a decreasing slope. 0 correlation, this looked a lot like what we had for our example here, just kind of scattered everywhere, just no real relationship. So this is R equals 0. And then the positive correlation, okay, nice and tight together here in a row where my slope goes up as opposed to the slope going down. R is equal to 1. -1 and 1, they're perfect correlations. So more than likely, we're going to find something like we did with the COVID data, where we find a number that's very, very close to 1. Let's take a look at another example. And the next example I'm going to take from this homework set in WAMAP. So we've got this linear modeling. I'm going to go ahead and just open up the exercises. And I'll do a teacher preview so I can see them all at once. And you can see here, this is just a good one to talk about. This one has a little bit of a positive correlation. The next one has no correlation, and then this one has a negative correlation. So, so a nice way to just kind of put those on that continuum between -1 and 1. Anything close to 0 is going to be no real correlation. Really wanted to look at this next one. So we've got some data shown below. We want to calculate the correlation coefficient, and I'm also going to, since I need to do it together anyway, I'm also going to find the regression equation. What I want to do is just to highlight the data. So I'm going to click, hold, and drag to highlight my data. I'm going to copy this, so Control C, just like I had done with my spreadsheet. I'm going to go into Desmos. That one. And I am just going to hide these. So if there's data that you want to keep, you can click on these colored circles to hide what you've got. I'm going to grab, let's get rid of this guy. I'm going to grab an empty cell and I'm going to Control V. Notice how it gave me subscripts of 2s. So if you have a couple of data sets going, you're going to want to adjust your linear regression formula so that it's grabbing the data that you want. I don't really care about the scatter plot here, so I am just going to blow right by the scatter plot, and I'm going to go ahead and put into the next blank cell my linear regression. So y2 sigma, so shift to get tilde, mx2 plus b. Nice correlation here. If I do look at this graph, I can kind of move it over here and maybe expand it a little bit. You can see that we do have a pretty nice negative relationship. And you'll notice that the R value, R squared, you can see how it is kind of helpful in terms of strength, but it doesn't give me the negative or the positive. So we're going to just be focusing on R. So we've got a pretty nice strong negative relationship, and I can go ahead and grab my parameters M and B to put into my equation. Let's make this small, and I'm going to go ahead and just write that into, if I can bring that back up. Well, let me just write it on our worksheet instead. So for that example, let me just move this guy over. I have a lot going on here. There we go. So I'm just going to write it down here at the bottom. Let me grab a different color pen. So this is for our homework example. We wanted the correlation coefficient. The correlation coefficient is negative 0.9829. You'd want to round that accordingly. If you were also asked for the regression equation, I would say that y equals m, and they gave me m as negative 2.13, or however many decimals you were asked for, negative 2.13x, and then b plus 32.11, plus 32.11. And that gives us the correlation coefficient and the regression equation with a really nice negative relationship there for that data.